welcome to the group exhibit Hydrogen, Fuel Cells and Batteries at the Aguerrevere 2017. We are here at the Technical Forum and my name is Muriel Buerkas. We start Wednesday's first presentation today regarding gPROMS simulation of automotive power plant system startup from minus 25 degrees with hydrogen combustion in stack cathode. Please welcome with me on stage Zbigniew, VP Fuel Cells and Batteries of Process Systems Enterprise Limited. The stage is yours. Thank you very much.
Hello, good morning. Yes, we are from PSE, located in London, and we are the modeling company. The modeling platform, the software platform offered by PSE is called gPROMS. It's called gPROMS. And as for fuel cell applications, the term modeling here covers things like mathematical modeling of physics, gas phase mass transfer, electrochemistry, capillary pressure-induced liquid transfer, liquid water transfer within a component of the stack, modeling of other components, units within the power plant system. And then with all these modeling components, we normally do dynamic simulation of the whole power plant system. There is also a lot of data processing involved for model validations, and the software has built-in functionality to do formal mathematical optimization of dynamic problems. And I dare to say that we must be doing something right with this modeling simulation technology, because Toyota and Honda became our key customers, and we've been with them happily for the last 7 years. We provide to them the software platform, the specialized libraries for fuel cells, software solutions, and time to time we do supporting projects for them. Now, just to give you a bit of flavor of what these big organizations can do with the help of this kind of technology, I give you in hands of Jorge. He will give you a few examples of within the, of course, the confidentiality allowed. So we are, Jorge will show a couple of things.
Hello. So I'm going to go a bit through the development lifecycle of our software and how it came to be what it is today. We were fortunate enough to begin working with our clients, with Honda, Toyota, at a stage where they were doing their R&D work for commercializing the fuel cell. So what they wanted to do with this software was process data, experimental data they had, and then use these models to explore the design space, pick the right design for the stack, and then work on designing their system in a way that they could commercialize it. So we started off by developing models to process data. So the tool has a way to input experimental data and a solver that tunes parameters in the model to match this experimental data. Once done with that, the models can be used to simulate a stack under very controlled conditions. So in a very simple system, and you can evaluate how the stack performs under many different conditions. And this is a stage where you can start making some design decisions with the stack. After that, you can move on to building the full-scale system. So, you know, what actually goes, in this case, into the cars. So this system here that you see here has all the components that you'd see in a car, from the hydrogen tank, you know, injector, ejector, the stack, air humidifier, air compressor, the whole system in one flow sheet, and you can evaluate how that behaves. This includes the control system, everything. So it's fully pressure-driven models that are controlled with any control strategy you like. And this helps evaluate how the stack performs. And finally, we also offer, you know, very high-fidelity 3D modeling of, you know, the microscale in the stack, so you can evaluate, you know, any reactant deficiencies and things like that. in the stack, and you can also see where water is condensing, how much is condensing, that sort of thing. So what I'm going to do next is talk about one case study. Obviously, we can't use any of the systems that our clients have. So this is going to use this case study using our own sort of theoretical system that we developed that comes with the product as a starting point for clients. And in this case, we'll be looking at how to start the stack from minus 25 degrees Celsius in a quick way by injecting hydrogen into the cathode line. So essentially, creating catalytic combustion conditions in the cathode catalyst layer. Now, the benefit of this, obviously, is it allows quick startup. However, there's many challenges. When you have a stack that's frozen minus 25 degrees Celsius, and you start injecting hydrogen, the temperature inside the stack will start raising. But actually, the coolant temperature going in and the coolant coming out will still be very cold. And so there's no way, really, to know what the internal temperature of the stack is during regular operation unless you embed thermocouples in the stack. And also, when you're generating so much water at these cold conditions, ice formation will occur, and you have to balance how quickly you start the system to avoid the ice becoming a problem or damaging your MEA. So this is the system we're talking about. So starting off, everything's frozen, minus 25 degrees Celsius. And right here, before the air goes into the stack, there's an injection of hydrogen into the airstream. So there's a mixture of oxygen and hydrogen going into the stack. This is a 3D plot showing the startup, where along this direction is the direction of coolant flow within the stack. And that's the time axis. So you see, initially, it's very cold. And as you inject the hydrogen, the temperature in the stack goes very, very high. So in this case, it's bad conditions. This could potentially damage your MEA. But measuring inlet and outlet temperatures of the coolant, you actually wouldn't know that the stack is so hot inside. So we used our software to evaluate different coolant flow rates, different conditions that you could start the system at, and studied this temperature profile in the stack at the end of your startup procedure. And what we found, for example, the black line is the case I was showing before, just now. So this is the temperature in the catalyst layer. You can see that it's got very, very hot due to the catalytic combustion. However, by altering the coolant circulation rate, if you make the coolant circulation rate very high, then it keeps the temperature across the stack very uniformly distributed. But the problem with that is that as the temperature increases, if you keep it all very cold, you'll generate lots of ice in the catalyst layer, which could damage the catalyst. So by adjusting the coolant circulation rate during this startup procedure, you can maintain the catalyst temperature at a level where the catalytic combustion will be fast due to the increased temperature, and the ice formation will be reduced thanks to the faster increase in temperature, but you'll avoid any very high temperatures that could really damage your stack. So the real benefit in modeling here is that as you model your system, you can look at the micro scale of what's going on in the catalyst layer, in your membrane, and really make sure that everything is safe, that nothing's being damaged. So many other things. Most of the work we do is concerned with water management within the full system, so how water stores in the stack, how long it takes for it to get out when operation changes, and really ensuring that the membrane stays well humidified the whole way through. We'll take any questions now. I think we're good with time.
Thank you. Thank you very much. One more slide.
Just a teaser, I guess, a problem we faced recently. A client was having a dilemma where they were increasing the catalyst loading by adding extra layers of ink to their catalyst, and they noticed performance started decreasing even with higher platinum loading. And so this is something that we figured out why it was happening thanks to the models, because we input the data, model tuned the parameters, and we were able to see the distributions within the catalyst layer explaining why performance starts decreasing when the catalyst, the platinum loading exceeds a certain level. So, if anyone's interested in discussing that further, we'll be at stand 65, E65 later.
Thank you very much, Jorge Aguerrevere.
Yeah.
Are there any questions from the audience right now? No, I would like to know more general. You have different collaborations with automotive companies, mainly in Asia.
Yeah, so it's mainly in Japan.
Japan.
Yes.
Do you see a difference how they treat the topic to Europe or to Germany, or what is your experience?
I mean, I think the biggest difference is the amount of investment that goes into it over there. I mean, Toyota is investing a lot of their own money into this development, and they've paid a lot of attention to this modeling tool. They use modeling quite a bit now that is going to really be commercialized. So they're using this for, ensuring safety, helping the lifetime of the stack, and reducing the costs.
Thank you very much.
Thanks.
If you've missed this first presentation and you're just waking up, you can also watch the presentation later on because it's live streamed and it will be available on the website. Thank you one more time. If you have questions later, visit their booth. Thank you.
Thanks.
We will continue with our next presentation at 10 a.m. about customized solutions for low temperature PEM MAA market requirements with a high plate. I'm very much looking forward to this presentation, and I hope you stay with us. Please have a seat, have some drinks. It's all on the house. There's coffee to wake up, and see you in a minute. Thank you.